This is the sixth and final video in the series building my own tiny tabletop hydraulic press. The leak I discovered at the end of the previous video was easily fixed with a new O-ring. I also attached the pump to the press and finished the steel a bit more neatly. I loaded the press to well over 6 metric tons to measure the elastic and possibly plastic deformation. To my satisfaction, the press held up very well under the forces occurring, and as far as my calculations are correct, none of the components are loaded heavier than roughly 1/3 of the yield point at these forces, F2 to F4 in this table. The pressure, see the graph below left, decreases by about 5% in the first 3 hours, probably due to the settling of the steel, and then remains almost constant. I am very satisfied with the total deformation of the press under this load. I calculated this, see force ST, at 1.74 mm under 6 tons, and the measurement results in 9% more. The difference between the calculated pressure without friction and the measured pressure, including friction, remains well under 10%. Let's give this little press some work. I have a hardened steel shaft, 30 centimeters long, that shows a slight warp. Let's measure and visualize the deformation first. Yes, this axis is clearly bent. It looks like a double deformation, a 68 micron bend evenly over the entire length, and on top of that, a 25 micron bend between 50 and 150 millimeters. Let us first try to eliminate this. The calculation shows that for straightening, we have to exert about 560 kilogram force at position 100 millimeters. Now to remove the general bend. Okay, I seem to have managed to get the curvature down to about 10 micron. Very nice, but I have to say that this footage doesn't tell the whole story. I had to try more than 20 times to sneak upon the final result with ever-decreasing steps, and I should have been able to see this coming if I had looked at my own calculations more carefully. A force of 1,866 newtons is needed to bend the axle just against the upper limit of the elastic deformation. On top of that, an additional force of only 31 newtons is needed to obtain the desired 68 micron permanent deformation. That is only 3 kilogram force difference, or 1.5%, between no permanent deformation and the desired results. And of course, if just a little too much force is applied, the rod is deformed in the opposite way. No, this method is really not recommended, and in my opinion, it is pure luck that I obtained such a nice final result. To expand the possibilities of the press a bit further, I made a few accessories. The first one you saw in the previous images, a screw in hardened steel cap with a slot for bending round material. Here I make an attachment for bending sheet metal. To be on the safe side, I add some completely unnecessary metal glue. I need 2 tons of press force to press the 16mm stud into the die. Pressing a press attachment with my press. Love it. Okay, that works as I intended. The next attachment is a bit more work. It will be an extension of the press to be able to exert pulling forces with it. I used the materials from my old primitive screw press for this. I cut 2 strips from the base plate for the pulling arm. A cylinder head, I screwed up, is sawn in two parts. One part becomes a holder for the load cell, and the other part gets M16 fine thread in which a tie rod will fit. After some more off-camera work, the pull attachment is ready. Let's see if it works as intended. The center of the rocker arm is exactly between the two pivot points, so that in this arrangement, the pulling force exerted on the testrode is exactly half the force exerted by the cylinder. This 8.8 socket head cap screw should offer more resistance. It has a tensile strength of almost 100 kilograms per square millimeter at maximum load. Just before the bolt snaps, it is necked to 2.2 millimeters in diameter, which gives a tensile strength of more than 200 kilograms force per square millimeter for this, at this point, extremely brittle cold-drawn steel. As a final test, I try to pull a stainless steel a 270 M6 bolt to pieces. Here, I use the other possible setup, where the ram is at one end of the arm, so the pulling force now has to be multiplied by 2 to measure the correct result. This measurement also corresponds to expectations. The A20 steel tolerates slightly less tensile forces than the 8.8 steel, but is much more elastic and stretches about 20% before snapping. And with that, we come to the end of this video, and the end of this project that has given me a micro-hydraulic press that is not only very useful for pressing in bushings and bearings and such, but with which also compression and tensile force measurements can be performed with some precision. I hope you enjoyed the videos and look forward to the comments. Until the next video,